Yes, Rohit, I've started.
Great. Okay, so let's get started without further ado. So, like I said, what we are going to do is cover supervised learning, unsupervised learning, and touch as much as possible on the deep learning in this lecture. So, with that, this is basically we are going to start this with the k-nearest neighbor algorithm and sort of give you a flavor. This is very simple algorithm to give you an idea as to how a supervised algorithm works. And for some of you who are curious, the implementation of this algorithm is on the DeepC website as well. So if you go to bit.ly/deep-c, you in the tutorial directory you will find the implementation of that. So I actually encourage you guys to look at that and see how this works in practice. So for the KNN algorithm, we're going to use IRIS dataset. This is almost 80-year-old dataset. It has about 150 samples. The smallest dataset I've worked on so far, and it does the job. And what dataset has is three types of flowers: Setosa, versicolor, and virginica. And these are shown in the right-hand side graph in the picture. And our objective of this algorithm is to find the the classification using majority vote. The way this algorithm works is you load IRIS dataset. It has 4 different features. Essentially related to leaf width, and so on. You load those 4 features in 150 rows, and that's your data set. And each one of those rows will have label, whether what kind of flower is that. So you load that data set, initialize the variable, and this is the main algorithm. When we say fit, that's the algorithm which we're going to explain here. So all essentially that algorithm does is you survey the opinions in the neighborhood, and then you compute the difference of opinion using simple Euclidean distance, which is nothing but x2 minus x1 whole squared under root, and then you divide that summit over all the samples. And then sort the survey based on the increasing order of Euclidean distance, and then you count top k votes. And you do that in the iteration, and that essentially is your k-nearest neighbor. So essentially what you're finding out, let's say in your neighborhood, you're going in your colony or your neighborhood and asking people who would they vote for? Would they vote for Modi or some other party, BJP, Congress, or whatever? Now you are collecting the vote, and to determine what kind of neighborhood that is, you would sort that using the formula of Euclidean distance. And if most of the votes come out on top as BJP, then that neighborhood is BJP neighborhood or a Congress neighborhood or whatever that is, right? So that's how it works. Now, you can go and check out DeepC to get a sense of how supervised algorithm works. Now let's look at learning algorithm, and this is gradient descent. You might have heard the name already. It's fairly popular, and essentially it is used to learn the features and parameters of a hypothesis of a machine learning problem or solution. So in solution, you create a hypothesis that this is my data set and this is what it looks like, this is what it should follow. And given that hypothesis, you want to find out what the numbers will look like. So who does the heavy lifting? Who does the work of finding those parameters? it is actually gradient descent that takes your algorithm, takes your hypothesis, and will try and find all the weights and biases of your hypothesis. That hypothesis can come in the form of an equation, or it can come in the form of a neural network or some other architecture. Regardless of underlying hypothesis, it does the job of finding the weights and biases. So the key point to note here is the gradient descent algorithm is an optimization algorithm that finds the parameters of a given hypothesis. In the right-hand side picture, what you see is essentially an equation which is to simplify this, the explanation of this algorithm. We have taken weight W1 and weight W2. And let's say this is your equation represented in terms of the surface. And the y-axis is your cost function. So cost function is represented in terms of W1 and W2. Now you want to find the minima, and you are at the top of this rim right here. Now imagine yourself in a weightlessness situation, like there's no gravity, and you are required to find the bottom of this surface. Now let's say this is a physical structure. If it was on Earth, you would start sliding, or catapult yourself, or do some somersaults, and the direction that fall will take you eventually get you to the bottom of that surface because of the force. And these points that you see are essentially your decision points during the what algorithm takes to reach to the minima, the local or the global minima of the surface. So you do that in the loop. So the entire algorithm is just one line: repeat until convergence, and then find the next weight. And this is next iteration, weight of the next iteration, or parameter of the next iteration is equal to parameter of the current iteration minus alpha. Alpha is a learning rate that we will talk about in a bit. And delta JW is essentially your slope of this function, or gradient of this path. So when you start, you initialize this from here, and then based on that initialization, and you assume some kind of a slope that this is the direction I want to go in. It doesn't matter. You can assume or determine or incorrectly initialize in the first iteration, and it will correct itself in the second and subsequent iterations. So initialization of the parameters and the slope does not matter in the first loop. The only thing it would affect is it might take more number of iterations. It may not be as efficient as an appropriate initialization. So you start that point and you choose that this is my next Wi plus 1 going to be based on the information that was presented in the last iteration and the gradient you chose. So you come here on this surface. This is the point, and remember the next point is decided based on the current and the slope between current and the next. So you come to this point and then continue making the same steps based on the slope or the gradient you see, and eventually you will find yourself in the local minima here. That's as simple as that. Now there are more hairy details of this algorithm and better versions of this algorithm. For example, stochastic gradient descent and ADAM and some other optimizers that do a better job than just simple plain gradient descent. But the idea is the same. You need the parameter value of the current iteration and the gradient, and of course a learning rate. ADAM optimizer will also adjust the learning rate as you go along, because in some of these cases, learning rate will determine how efficient, how fast you can find the local minima. And the thing to notice here in this equation, delta is a vector of partial derivative of cost function. And we will talk about the cost function in a minute. But that's the whole equation of learning algorithm. And this is an example, essentially displaying the choice of learning rate. And again, this is also an example that I can sort of pass a notebook to you guys later on if you're interested. But what this is an experimentation given a hypothesis. If you vary the learning rate, would gradient descent find a value, and how quickly will it find it? So these are number of iterations. On the first column, you have learning rate, and the second column is number of iterations. And now you see the final value and accuracy is determined based on the learning rate. What that means is you might be able to find an accuracy that is not acceptable if your learning rate is large or very small than it's supposed to be. So what the thing that I want to draw your attention to is look at the variation of learning rate from 1e to power minus 1 to 1e to power minus 5, and then look at the accuracy. How does it change? It starts with the point that it's not able to achieve the accuracy to a point that it goes to excellent quickly, and if we continue to increase, it goes to good, fair, okay, and then again not acceptable. So it becomes unstable at some point if you increase the learning rate more than the required value. So this is called hyperparameter, and it's part of it's very important part of hyperparameter tuning. In AutoML, it is done automatically for you. If you're designing your own network or your own hypothesis, you're supposed to find that learning rate on your own. And it's kind of an art to find which one would work best. Eventually, if you've done enough experimentation, you will find the window that'll give you an idea, the way it will work. What I would suggest for beginners, you should take a window anywhere from 1e to power minus 3 to 1e to power 2 or 3. And in that 6th order, you will find the one order which works best, and then you go deeper down in that one order. Pick that order. Let's say it's working pretty good between 1e to power minus 3 and 1e to power minus 2, and then you go and perform another 10 iterations on few samples, and then find which one is working good. So it's kind of a discovery process, generally, unless you're using AutoML. So one thing to note here is gradient descent is a simple algorithm which gives you parameters for the next iteration. Parameters, when I say parameters, I generally mean weights and biases for the deep learning, and parameters for the machine learning hypothesis. It's the same algorithm that is used in both. And this shows your fx. So this is one fx that I hypothesized. This is my machine learning hypothesis, and how the derivative of that looks like. So I've drawn the derivative of that, and these points are essentially the points chosen. The blue points on the curve are essentially the points chosen by the gradient descent. Now, on this screen, on this slide, I want you, there are a couple of, there are few points, like close to 25 points that are scattered all over the screen. I want you guys to look at that for 5 seconds and guess what kind of model would that be? What kind of equation does it fit in? And it's a simple 2D where you have a dependent variable on the x-axis and independent variable on the y-axis. And if you see the bounds, it's -1 to sort of kind of +1. So that's the the model you have. Let's say somebody gave you this data set, and they want you to find a machine learning algorithm that can predict the next point. So let's say after 1, what would be the value of y given x is 1.1? And this is your data set, and you know nothing about any other. You know nothing about data set other than what you're given here. And so that's a classical machine learning algorithm that you have to design. So by now you should have at least have a guess that this is some kind of a curve, and that curve essentially is your sin x. So what I did here is I gave y-x is equal to sin 6x, and with the 15% of random noise. And so I used this equation and I injected 15% random noise and came up with these points. So if you see these two, here it's slightly difficult to see that this is a sine 6x curve, but once you draw that, it becomes fairly easy to understand. Now, why that 15% random noise is because that's how real world works. When you're observing a certain phenomena, you will have some kind of a noise. You won't be able to measure that accurately. So expect some kind of noise in your data sets, and machine learning should be able to deal with the noise you have in your data set. So that's that. And with this graph, I'm going to explain three important issues or important problems that show up while creating or debugging your machine learning or deep learning algorithms. So first one is underfitting. And what I'm trying to show here is underfitting with a linear model. Now, given this data set, let's say of 25 points, you somehow assume that this might be a line. For example, this line somewhere here might represent this entire data set. Now, if you do that, and this is what this gradient descent comes up with. If your hypothesis is aligned, it'll do its best to find the parameter for that line. And line is simply y is equal to mx plus c or mx plus b, depending on which continent do you live in. So c is an intercept on the y-axis, and m is the slope. So there are only two parameters on that hypothesis. And machine learning algorithm will find so that the cumulative error of this line with respect to all the given points is minimal, right? So what it is doing is actually finding out the error from this point to this line as to this line would predict the point here given this x value somewhere here, and this is the real x, so that there is an error, right? So what it does is it finds the error and cumulates that error and tries to minimize error for all the points. And that's your cost function for this machine learning hypothesis. Now, minimizing cost function is the job of a gradient descent algorithm. Now, you might have easily guessed that the linear model does not have enough order, enough power to predict and reduce the accuracy, however hard you try. It's the same gradient descent algorithm. You might run 10 epochs, 100 epochs, or 1,000 epochs. It doesn't matter. The line would stay aligned because you have asked it to find the parameters of a line. So with that hypothesis, it will do the best, but the hypothesis is not correct, can't do much. And that's where the concept of underfitting comes in. In this, it's easy to see that your model has a poor fitting. The accuracy, prediction accuracy would be very poor because, for example, like I said earlier in the lecture, if you have x is equal to 1.1, your prediction would be far off, for example, somewhere in the range of -1, where it should be positive, somewhere close to 0.5. And that gap would continue to increase beyond this data set. Either it will be very high if your x value is negative, or very low if your x value is more than 1. And that's where you say when your training accuracy is not giving you is poor essentially, and the test accuracy is even worse. So with these two issues, you can easily classify this issue as an underfitting. And so there are ways to address underfitting. I'm not going to cover these. Essentially, depending on your experience, you would want to change something. The first thing I would change is the model order. So instead of coming up with y is equal to mx plus c, I'll say, okay, let's go with order of 5. And a line is the order of 1. So in this model order of 1, you can only do this much. And if you give it, my hypothesis is somewhat like y is equal to w1x5, w2x4, w3x3, w4x2, and w5x plus bias. And with that equation, if you provide this equation to as a hypothesis to gradient descent, it might be able to do the job. So the first order of thing is to check your hypothesis. And then there are other things like you might want to reduce learning rate if training has wild fluctuation, and of course change the model, try a new model, linear to polynomial, or go for deep learning, and so on. So that was underfitting on a data set of 25 points. And for overfitting, it's the same data set. What I've done is I have provided I've chosen machine learning. I went overboard and I said, okay, the line isn't a good fit. It's an order of 1. Let me start with model order of 15. So I go overboard on hypothesizing my machine learning model. Now, what the algorithm does is now it has a lot of flexibility and freedom to find an equation that goes through each and every point. So what gradient descent will do is will find the slope and your weights and biases parameters in a way that it goes through all of these points, or at least most of these points. So it came up with this weird looking curve, which has very minimal accuracy within the window of 0 to 1.0, because that's the limit of your data set. Your data set values are between 0 and 1.0. Now, this model, as you can see, is clearly not a good result. It'll give you incorrect results between, let's say, 0.2 and 0.4, because the curve is wildly fluctuating. And there are not enough points between 0.2 and 0.4 to guide gradient descent and stay within the bound. So there are two problems with model order 15 hypothesis. One is you don't have enough data set samples. The second one is the model order is really high than it should be. And this is called overfitting. It's overfitting the data set. And so the idea of machine learning hypothesis is generalization, meaning the architecture or hypothesis should be able to generalize your predictions beyond what is present in the training data set. So when you go to test, it has generalized well enough. So if you're getting 97% on training, maybe 95% or 98%, or somewhat within a reasonable range. That reasonable range generally is plus minus 5%. You can stretch it to plus minus 10. Anything beyond that is an issue in your training. So overfitting results when the model learns patterns and attributes of the data set with high variance along with those of noise and outliers. It achieves a good accuracy of the training set and performs poorly on the validation set. And again, there are ways to address this overfitting. You can simplify the model. In this case, I'm going to reduce the model order to 5 and see what happens. Yeah, for example, if you have, let's say, 10,000 samples, then this would have done much better on even model order 15 hypothesis. And you might want to use techniques like regularization and drop-off, which takes care of some of these issues. But every technique you will use will have its limit. And the issue you have to find actually comes from experience. Once you start dealing with these problems, eventually you will find out, oh, this is underfitting or overfitting. Initially, finding and labeling if the issue is underfitting or overfitting is hard enough. It'll require you to reason, for a few minutes or few hours to find if this is really underfitting or something else is going on here. So what if we increase the data set size, right? So I increased from 25 to over 1,000, and this has enough sample points for us for even a model order 15 model to find the regular pattern here. And effect of increasing the data size, even on, like I said, on model order 15, it does a fairly reasonable job, right? So what you find from this discussion is a size of data set, number of samples in the data set, along with your hypothesis, will collectively determine the accuracy. It's not your learning algorithm alone. So there are multiple variables that are affecting the accuracy of your training. So you should keep that in mind. And this is summarizing the results of what we've discussed in the last 15, 20 minutes. Essentially, machine learning algorithm is expected to generalize the patterns seen in the data set. And on the left-hand side, you see underfitting. In the middle, you see well-generalized model of order 5. And on the right-hand side, you see overfitting. So remember these three concepts when you run into issues and your accuracy is not to the par where you would expect. Generally, even for a binary classification, if your accuracy is under 70%, it's really poor model. So I haven't seen any paper being published on 70% or under 70% accuracy, even on a binary classification or prediction. So unless it goes to 90 or 90 plus, depending on the type of problem, type of data set, and the things, it might be a significant discovery. So remember, accuracy, improving accuracy is the first order of business for a data scientist. So I'm going to start regression. But before that, just wanted to make sure what we have covered. We have covered KNN, and I'm going to drop a link to you in the Discord channel pretty soon. And we have covered gradient descent, the algorithm, the way it works, and also 3 issues that are frequently found during the training, which is underfitting, overfitting, and proper fitting or generalization, right? So with that, supervised learning has 2 different flavors. One is regression, which is a form of prediction forecasting, and the other one is classification, which is finding what kind of class does this sample belong to. And remember, this is a supervised. These 2 are supervised algorithms. So that what that means is you need a labeled data set. So every sample in the data set must have a label or a value. If it's a regression, then it will be a value. For example, you're trying to find the value of a house, which is a classical problem discussed in the literature of finding house values in the neighborhood. And that would be it would be a prediction of continuous values depending on the parameters of the house, like how large the house is, what is the square footage, how many rooms, what kind of kitchen, how large is your front yard, backyard, your garage, and how nice is your bathroom and stuff. So depending on a lot of those parameters, it can give you a value, and that value comes from mostly a data set which has information on, with these features, what are the other houses that have sold in the neighborhood. So that's regression. Formally, it is known as class of supervised algorithm that attempts to establish a continuous relationship. And mark my words, continuous relationship. And that is one of the differences between regression and classification. So continuous relationship between one independent variable, usually shown on y-axis, and set of other independent variables on y-axis. Excuse me. Yeah, so that's regression algorithm. And these are some of the norms that are used as part of regression: L1 norm, L2 norm, LP norm. And what L1 norm is essentially given 2 points. What is the summation of absolute values? An L2 norm is essentially your Euclidean distance. An LP norm is a generalization of L2 norm for a pth power. And we are not going to cover these algorithms, but if you have time and would like to find more, then you should do research on your own. I can provide some literature, but these are some of the good algorithms to go through as a classical algorithm. They're not used as much, but it'll give you a good idea as to what machine learning algorithms look like and how did they evolve since 50s to what we have today. And especially Ridge and Lasso, they are sometimes used, but again, you will go through the kind of issues these algorithms had and how did they improve one over the other, and what kind of thought process went into addressing some of the issues like variability and high bias in some of these, and that would actually orient you towards discussion when that issue comes in deep learning. So let's say your network is starting to exhibit a high variance issue. You would understand much more how to change some of the parameters or hyperparameters to address that and why that would be effective. Understanding that on deep learning would be difficult because deep learning has sometimes millions of parameters that is hard to put your head around as to which one is affecting what. So if you start with two variable problems or single variable problem and apply lasso or ridge regression and run into that issue, it's easy to understand. So we're going to not cover the rest of these algorithms. And some of them are actually discussing the issues that you would run into if you were using these algorithms. I can give you the keywords. For example, regularization is practically used in deep learning as well. So if you have time, you try and understand what regularization means and how does it address overfitting. In summary, regularization is in the context of deep learning is it has several functions. So dropout is one of the popular form of regularization, and what dropout does is it would randomly drop out some of the weights that were learned. So you might have W99 that came up to some value, and the dropout would say, I'm not going to take this value randomly. No principle set on that as to why it is not using that value or will continue to use the older value, and it just works out good and well in statistical algorithms. So that's dropout, and that's how regularization typically works. There are other functions for regularization. So you have L1, L2, LP, and so some of these algorithms are used in deep learning training. Okay, so we are going to, and bias and variance, that's another issue that you should familiarize yourself. Quickly, we are going to cover, let's say, bias and variance for a given model. Let's say you have your machine learning hypothesis or a model that is fixed, not going to change. If you increase the model complexity, then initially the error will start to come down, and after a point it will start to go up again. And that generally is the bottom of the error is the intersection of bias and variance. So high variance is a bad idea, high bias is a bad idea. Both of them should be optimal, and that would be reflected in your error. So keep that in mind. Bias and variance have inverse relationship generally given an optimum model complexity. So I'm going to skip some of these and move on to classification. Okay. Now, so that was regression. And regression, like I said, it provides a continuous value, like house values is a classical algorithm, classical problem that's That's covered in most literature, most books. So it'll be helpful for you to go through that because you can easily relate to house features and the values. Now come to classification. Classification is a process of arranging object into taxonomic groups according to the observed quality and characteristics. So that's a textbook definition. In the spoken words, what it is you come up with discrete values of classes. And the classical example of that is hand digit recognition that I guess we have gone through that example already. So you are writing a digit, a machine learning algorithm will try and identify what kind of digit is it. So given the type of digits, single digits, there are only 10 for a base 10 number. Now, so that means that you have 10 classes. What that means is you have created a single digits class and divided that into 10 different classes ranging from 0 to 9. And so it's an instance of supervised algorithm that attempts to establish a discrete relationship between dependent variable, like an image, handwritten digit, a grayscale image of 28 by 28, to an independent variable. And that variable is finding out what the class is. Is it digit 0, digit 1, digit 5, 7, or whatever, right? And one important point I would like to make here is that you can convert any machine learning problem from regression to classification with a concept called decision boundary that we're going to cover soon. So the hypothesis might be same. You will have the same feature set, and depending on the cost function, if you have cost function as mean square error, that would be your regression. If you change that to softmax, then it becomes classification. So again, few things about regression versus classification. You might have the same machine learning hypothesis just by changing your cost function, the way you are labeling or predicting. The output will change problem from regression to classification in terms of solution, and in terms of conceptual classes. What you need to come up with is a decision boundary to create those labels for the class, right? So, for example, house price prediction, right? It's a regression problem because you want to find out what is the value of this house, right? Now you can convert that into another problem to find whether this is what kind of house this is. Meaning, is it low income house? Is it medium income house? Or is it a posh community or a posh house? Some kind of class which classifies that this house is has that class, right? And you can come up with that class by creating a boundary. So let's say you can say house that is sold under 200,000 is a low income house, 200 to 600,000 is medium income, 600 to 1 million is about high income, and then beyond that it's a posh or high income community or high income house, very high income house, something like that. So you created 4 classes based on those 3 decision boundaries or 5 decision boundaries, depending on how you create the boundary. So again, the point here is that you can convert any machine learning problem from regression to classification with a concept called decision boundary. And the classification started from logistic regression. And logistic regression, I'm looking at my watch, it's about 75% there, so I have 15% or 25% more time left. So I'll try to cover as much as possible in the classification, and then we'll leave the deep learning for the next lecture. So logistic regression is widely used to predict the binary outcomes. And the S-shaped curve is essentially your probability of, let's say, passing the exams given the number of hours studies. So let's say you want to create a model based on your study habits, and if you do not study, what is the probability of passing the exam, versus you study over 6 hours on the same day, what is the probability of passing the exam? Now, the number of hours studies is captured only during the exam day or a day before that in the last 24-hour period. That doesn't, this data set does not capture whether you studied the year around, right? And so this is in some sense incomplete data set, but again, it has enough information to come up with a model. Now that model may not be highly accurate because data set does not have enough features, but it's good enough to explain the idea of logistic regression. So essentially, based on number of hours studies, it provides a probability of passing the exam. And by passing, that means is whatever your university or college has determined. It could be 33%, it could be 50%, it could be 66%. How do you pass the exam, right? So that boundary is decided by that policy. Now, whether you would ace the exam, will you get 100% or 80%, is not the concern of this outcome. It's barely deciding whether you will pass or not pass. And so this simple model, given the independent variable of number of hours studied and the probability of passing the exam, is dictated by cost function called logistic regression. And there are a lot of use cases of this, whether, for example, if you go to a bank, based on your feature set, for example, how much money do you have? Do you have 5 houses, 3 houses, no house? How much money do you have in the bank? Do you have a job? And so on and so forth. They would loan they will sanction the loan or will say you're not qualified. Spam filtering, like Gmail, for example, will put one of the emails in your spam folder or will let it go through in one of the labels, for example, inbox or updates or whatever have you, right? So there are a lot of use cases of that classification. Real life scenarios, cancer prediction, whether it's malign or benign. Weather forecast is going to be sunny, rainy today. This slide explains the sigmoid probability, meaning your threshold value. Now, you might have a different decision boundary. The threshold value is the same thing that I was calling decision boundary in my last slides. So number of hour studies gives you a probability. If the probability is, let's say, 0.29, you are saying my threshold is 0.5. So you will say, no, this person is not going to pass based on the information of number of hour studies. And the optimal value comes around 3.5 hours. So that's your decision boundary, right? And beyond that, you say, okay, this person will pass versus this person will not pass. And that's called sigmoid probability. And there is a theory called maximum likelihood estimation. It's a probability model to detect the of likelihood of something happening. So in simpler words, without getting into MLE theorem or some of the complex mathematics underneath, it essentially predicts, gives you a kind of probability whether the student will pass or not. And that's called logistic regression. That cost function is called logistic regression. And this is essentially your logistic regression equation, meaning you start with the equation of straight line, and that could be one model. The other model is why you're saying your value, your outcome of the model is limited from 0 to 1 for this equation. So W times X plus B, typically if X is infinite, Y would be infinite, right? Because it has a linear relationship. Now you want to limit that. Now, why are we talking about Y is equal to WX plus B? Because we are trying to explain the concept of logistic regression. How do you take a model and convert that into a probability? So we are taking the simplest model here, the linear model, and trying to find the probability. So W times X plus B is bound between minus infinity to infinity. And if you want to limit that to 0 to 1, you have to transform this y to a cost function somehow. And y over 1 minus y is one way to do the same thing. And the reason be that if your y is 0, then it comes out to 0. And if it is infinity, then it is 1. So the range is y range is 0 to 1 if your x range is 0 to infinity. So it limits this function, this particular function y over 1 minus y would limit your outcome of dependent variable y between 0 to 1, given regardless of the value of independent variable x. And this is what we want. We are actually looking for a function to bind in the limited range. And so transform it further to get the range from minus infinity to plus infinity is log of y over 1 minus y. And that's the final logistic regression equation. So you see the kind of sort of thought process behind it. There is a derivation that I've avoided, but the thought process of converting large value and limit it between 0 to 1 to find the probability is actually a logistic regression cost function, which is given by log of y over 1 minus y. And we'll use some of these in our examples next week. So the sigmoid probability is given by a sigmoid function, which is 1 over 1 plus e to power minus t. Minus t is your independent variable like x, and it has the same the same properties of binding or limiting the y value from 0 to 1, just like log of y over 1 minus y. So that's another probability that is used, and sigmoid is used to date in binary classification. If you have multi-class classification, generally softmax function is used. Now, the other point which is very important for you to understand is for classification, accuracy is not sufficient metric to understand the value or value of a model. And so what we use is something called F1 metrics or confusion metrics. Now, disregard this slide for a moment and be with me on my words. So let's say you're trying to come up with, I'm just giving an example as to why accuracy is not good enough criteria for classification for certain cases. And what metric would be useful is case-by-case basis. Now, I'll give you one or maybe two cases to explain my point, depending on the time we have. So let's say you're coming up with the model that that is class based on certain information. Let's say machine learning model that I would like to give it to you because it does a better prediction of whether a patient has cancer or does not have cancer. And the doctor will start asking questions, right? Now, one of the questions, if I were a doctor, will ask you, okay, so I have 1 million patients that are coming to see me or see our hospital every year. And out of those, we only find 50 cases that are really have cancer. So it's a very small percentage of the total population that will have cancer. So this is an imbalanced data set, meaning your negatives, meaning people who do not have cancer, is very high, and people who have cancer is very low. So this is called imbalanced data set. Now, if you say, for example, that if I write a one-line program which says the probability of anybody having a cancer is 0. Correct? Now, what is the accuracy of my algorithm? It's 99.5%, if I did my math correctly. So it's essentially 1 million minus 50 divided by 1 million, and whatever that number comes out to be. It's either 99.95 or 99.5. Very high number is the point. And you go and tell the doctor that I have an algorithm which is predicting, the outcome with the 99.95% accuracy. They would not take that number. They will ask you, so what happens to those 50, right? And of course, you have 1/9 algorithm which is saying nobody has cancer. So then you will say, yeah, but 50 it's only 50 people that I'm wrong on. I'm correct on 999,000 and 950 people. Isn't that good to you? He will say, no, this is a bogus thing, right? And rightly so, because in the field of healthcare, you want to find out everybody who has a disease or a problem. Maybe you might want to go overboard, and instead of 50, you might want to predict 100, and say these 100 might have cancer. Because if they don't have cancer, a doctor will eventually say, go home, you're fine. And that is okay. They spend few hours, maybe some resources and some money to eliminate that person. But on the other case where you say none of these guys have cancer, then there are 50 people who went home with that confirmation and eventually died or something bad happened, right? And that should not happen. And that's the value. And from that, you might want to derive that your false positives are okay, but false negatives should be 0. And what that means is false and negative, meaning you are saying that this person does not have cancer, where he does. That's a false negative. And in the case of cancer prediction, it should be precisely 0. You don't want anybody to go home if they have a cancer. You might want to detain some people and go for further screening, and that's false positive, meaning you're saying this person is cancer positive, which is false. So based on this discussion, the accuracy is a bogus criteria for classification. And another example, which I'll be brief about, is a fraud detection. So your credit card companies and bank, they are regularly, and they're very they want to find out if a transaction is a fraud transaction or not, right? And given again the same metric of 1 million transactions, they are fine catching some transactions which are not fraud, and they can put few people for further questioning, further screening, if the person who's doing the transaction is a valid person or not. Now here the caveat is it's not as valuable as healthcare example, because credit card companies, they don't care if somebody is doing the fraud of $5 or $10. And the reason being, the secondary screening of calling a person and questioning them or alerting them will cost them some money, and that might be in the range of $10 to $50. So the objective of these banks is to continue making money and not lose any money, right? So if in this transaction they're losing money, that they're fine with that kind of false positive or false negative for that matter. The value for them is if there is a transaction worth $1 million and that is likely to be fraud, they want to catch that transaction and put more people so that they don't lose money. So the point of bringing the second example, and I'm not going to get into detail, you can actually reasonify based on my first example, that the values for this second class of problem of fraud detection is very different than the healthcare example. So the classification does not have a silver bullet how to measure the value of a model. It goes case by case basis. And with that, I would actually end now. I have a couple of minutes that I can spare. In the next lecture, we will finish this with an example and go through some questions and finish the supervised learning, and then we'll go through deep learning. So now I can take questions if for